Okay, hello, welcome. And if you missed the lesson in class, here it is. I'm going to put it on YouTube and you can look at it at your leisure. For today, what we did was we defined the following terms in our notebooks: nebular hypothesis, hydrosphere, atmosphere, biosphere, geosphere, and solar nebular disk model. You're not going to find the last one in the book, so I'll give it to you at the end of the presentation. Now, what I did was at the end of the presentation, I have all the definitions for these terms, so you can wait until the end to write them down. You don't need to take any notes on the presentation itself from today, because what I did was I wanted to tell a story, because I think sometimes in science we lose the story aspect of some of the things that went on that make them interesting. In a regular science class, you might have a teacher who just says, hey, the Big Bang Theory was this, and some guy predicted that the photons of light from the Big Bang would be coming back to Earth in the forms of microwaves because the space is expanding, whatever, 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 and then just move on. And there's actually a really cool story and a cool term I like to associate with this story. So let's try this and see how it goes and see how you like it. Okay, how we think we got here, because obviously we don't have a recording of anything. Everything is based on observations and calculations that we do. And so here's just some things you should know about the Big Bang. First thing, you need to know what the word serendipity means. I asked my students, nobody knew. I asked my students if anybody had ever heard of the phrase serendipity. A couple of them raised their hands. Maybe they saw, I think possibly there's a rom-com called Serendipity, which would make sense when you see what the definition here is. Serendipity is the unexpected discovery of something wonderful, often while you're looking for something else entirely. So you could see how that would lend itself to that. But it also happens in science quite frequently. Okay, remember, you don't need to write any of this down. This is not going in your notebook. But for the Big Bang, the mainstream consensus today is that the universe erupted into existence about 13.8 billion years ago. There are some scientists today pushing for a 27 billion year old model, but we'll see how that goes. Before that, we think there was a singularity that contained all the matter in the universe in an object the size of possibly a proton. I think this has been revised down over time. I think I first heard this was like everything in the universe was the size of the Earth, then a cell, then an atom, and now maybe a proton. That singularity would be approaching a point of having no volume and nearly infinite density, which is probably impossible, but who knows? The laws of physics might not have applied back then before the Big Bang. If you wanted to observe the singularity and then the Big Bang that's about to happen, you'd need to retreat to a safe place to observe, right? Except there is no safe place. There is no place. There's no where. When the universe expands, it isn't filling up the space. It's actually creating the space as it goes or expands. There's no outside the universe. There's no time. There's no past. There's nothing. There's just nothing. There's nowhere to be. So you can't observe it. But then from nothing, boom, the universe begins in a single blinding pulse. The singularity expands faster than anything you can comprehend, faster than the speed of light, because that's not a rule at this point. In the first second, which the first second of existence of the universe is probably one of the most contested seconds in science that scientists will ever look at. People spend their whole careers examining this very, very, very brief amount of time during the Big Bang. And we think that during that first second, we probably got gravity, we probably got the strong and weak nuclear forces and other forces that govern physics. And in less than a minute, the universe is already a million billion miles across and growing faster. Mind-boggling. In about 3 minutes, heat from the Big Bang has produced like 98% of all the matter that there is or will be. While the early beginnings of the Big Bang Theory have been around since the 1920s, this was first suggested by a scholar priest named Georges Lemaître. I don't know if I'm saying his name right. If you know it's different, please comment below. But it didn't become a really active idea until the 1960s. when two young radio astronomers made an accidental discovery that would change the face of science. So here we go. Here's the story. We'll start at Princeton, 1965. There was a team of scientists who were hard at work on an idea that had actually previously been suggested by a Russian scientist named George Gamow. He claimed that if you look deep enough into the universe, you should find some leftover background radiation from the Big Bang. Gamow calculated that the radiation would reach the Earth in the form of microwaves. Okay, but how do you see them? How are you going to detect this? The Princeton scientists, they had actually come up with the same idea independently, but nobody had read any of Gamow's work or any of the follow-up work, because I believe in some of the follow-up work that other scientists that looked at Gamow's work actually suggested that there was a radio telescope that's just down the road from Princeton, an hour away, that would be suitable for this. And there we have a picture of it. So at the Bell Labs in Holmdel, New Jersey, you have two scientists, two radio astronomers, Penzias and Wilson. They're attempting to calibrate the radio telescope for use in detecting faint radio signals in space. Everywhere they pointed it, though, they kept picking up this background hiss. So they examined their equipment, made sure everything was orderly, and they found a pair of pigeons living in the horn, and so they had to remove them, take them far away so they wouldn't return. Then they had to clean out the pigeon poo because pigeon droppings were in there, and they referred to this in their paper as white dielectric material. That didn't work. Then they aimed the horn up into space to try and eliminate the hiss away from like New York City, I guess. That didn't work. They aimed it in all these different directions. That didn't work. Nothing worked. So stumped, they reached out to another radio astronomer at MIT, and I believe that guy, he determined like, oh, this is probably cosmological in its source. It's not coming from the Earth. So he referred them to the Princeton team. So back at Princeton, the head of that team gets this phone call from Penzias and Wilson. They describe what they're hearing, and when he gets off the phone, he looks at his team and says, well, boys, we've been scooped. Because what Penzias and Wilson were hearing, this was the background radiation predicted by Gamow, the first photons of light returning as microwaves. So one journal in Science had two articles in it. Penzias and Wilson wrote one, and in it they described their experience with the hiss and how it was isotropic, which means coming in equally in all directions. In the same journal, the Princeton team published an article explaining how this was the background radiation from the Big Bang. That Princeton should be capitalized. Here's where the serendipity comes in. Penzias and Wilson did not know what they had discovered. They weren't even looking for it. They didn't explain what it was. In fact, they didn't even realize how important this was until they read about it in the New York Times. But in 1975, they were awarded the Nobel Prize in Physics. Go figure. What did the Princeton team get? Nothing, but a well-earned pat on the back, probably. So we can actually hear this background radiation. If you turn on a TV and go to the antenna mode instead of cable, or turn to a radio station and go to a station where there's no broadcast on, you'll hear static. 1% of that static that you hear on the radio or see on the TV is from the cosmic background radiation. So the next time you're scrolling through the TV and there's nothing on, you could be watching the birth of the universe. Just saying. And the universe, we're very lucky the universe formed the way it did. I mean, obviously we're here, right? But there are some scientists who say that, while it formed, if gravity were a little stronger, a little weaker, maybe the universe wouldn't have formed, the way it did. Maybe it would have formed too slowly or too quickly. We might have everything spread out too far to form anything, or maybe it just collapsed back on itself. And you know what? There are some scientists out there that say that that's actually what has happened. Could be what happened. A Big Bang happens and gravity's too strong and it just collapses on itself, and then it happens again and it's a little weaker, but it still collapses on itself, and it just keeps happening until boom, we get to the one we're in now, and we're all here, and maybe it's perfect, maybe it's not, maybe it's going to collapse one day, maybe it'll stop. Who knows? We do have one problem though. We believe the formation of the universe resulted in the formation of hydrogen, helium, and lithium. So how did our planet get here, having all the elements, naturally occurring up to 92? with a few exceptions. How do we get here? Where did they come from? That's where we get to the nebular hypothesis. Now, you may have heard this referred to as the nebular theory. In fact, back in 2002, Holt, Reinhardt, and Winston produced a book called Modern Earth Science. And in that book, I taught out of that book. That book, it actually does refer to it as a theory, but some people say that, and this was done by a guy named Laplace, and we're going to talk about him later, that theory, that idea, didn't actually make any predictions that were testable. So you can't really call it a theory because it hasn't been tested. So maybe it's more appropriate to call it the nebular hypothesis. And here's just a quick breakdown of it. So you have this dust cloud in space with all these elements in it, and lithium, hydrogen, helium. And as they start coalescing together, it starts rotating. And as more and more material gets pulled in, gets packed closer together, the temperature goes up. And as the temperature goes up, the rotation increases. And eventually, the nebula flattens out into a disk. And everything goes in the same direction. And if you think about it, if you look at the planets, they're all going around the sun in the same direction. So the sun forms in the center of the nebula. Dust particles in the outer regions combine to form planetesimals, which are only a few kilometers across. And then they combine and collide and form the planets. And that's the basic idea of the nebular hypothesis. So here's a video I found online of a teacher who tries to demonstrate this with a water balloon that he attached to a drill. It looks like he's using duct tape. I have not had a chance to try this yet. I would need to go and get some balloons and set this up. And it looks like the bucket is actually very important, as you will see. Here we go. Right. Oh, universal clone. Yeah, wait, let's skip on to the next one. There we go. So that's pretty cool. It's cool the way that flattened out like that. So that's where they think our nebula did, and that's why we have the solar system that we have today. So that last definition for that one that was not in the book, here it is: the solar nebular disk model. This says that the solar nebular disk model is the leading theory for how our solar system formed. It proposes that the sun and the planets formed from a rotating cloud of gas and dust called a solar nebula, which we think collapsed under gravity about 4.5 billion years ago, flattening into the disc-shaped structure that we have today. And we see this in other areas in the galaxy where we see nebulas that look like they're starting to take on this dish. We're never going to actually see it go soup to nuts. It just takes too long. But we see like the stages of it happening in other places. And then let's see here. Go to the next slide. Okay, so here was the definition for hydrosphere, if you need to write this down. The hydrosphere is a dynamic mass of liquid that is continually on the move, evaporating from the oceans, going up into the atmosphere, precipitating out of the atmosphere and falling back down to the land again, and then running along the land back to the ocean again. We have the atmosphere. That's the life-giving gaseous envelope surrounding the planet. It's very thin. And then we have, come on. Well, I guess that was the last one. That was it. And that was the presentation for today. So if you watch this, you got the definitions down, you're all caught up. We'll see you in the next class, and have a good day and have a good weekend.